Section 5.3 is evaluating definite integrals, and we'll actually see indefinite integrals within this section as well, and we'll get that definition when we get to it. So this is sort of one of the two parts of the fundamental theorem of calculus, this evaluation theorem here. It's probably one of the most important things in the course. It's a connection between integrals, definite integrals from a to b. Remember that this expressed the area between the curve f of x, the graph of f of y equals f of x, and the x-axis along the interval from a to b on the x-axis. And we had a means of calculating this for simple functions, namely low degree polynomials like x squared and x cubed. But we found that that's a pretty tedious scenario if we remember the problems of section 5.2. So this theorem is actually quite powerful. If the function in this integral, lowercase f of x, is continuous on the interval a to b, and that's a closed interval a to b, so it's continuous at a and b, and lowercase f happens to be the derivative of capital F, so in other words, capital F is the antiderivative of lowercase f, well, then the integral, or the area between the curve f of x, y equals f of x, and the x-axis between a to b is given by this difference of the antiderivative f of b minus f of a. So that may be okay. Talking it through sounds fairly complicated. Let's just look at what this actually means for our calculations. So we're asked to evaluate the definite integral, and well, we see we're evaluating 2x cubed. Now this dx we'll think of as telling us which variable we're integrating with respect to. That's one way to consider the differential dx, because it is still the differential dx that we know from chapter 3 a while ago in the course. What it's really doing is sort of, one way to think about it is it plays the role of delta x in our rectangle widths and our subinterval rectangle endpoint approximation. So 2x cubed is a polynomial, so it's continuous everywhere. Specifically, it's continuous from 0 to 2. So that means we can use this evaluation theorem up here. Now, it's important to check that those conditions are met, that the function's continuous on the interval. And I believe the last example in this set of notes will show us why we need to do that and what can go wrong if we're not careful about it. So the integral, by the way, from last week's or last section's properties, we know that we can factor constants out of integrals. So I can factor a 2 out of the integrand altogether. So the inside of the integral, the function that goes in here is sometimes called the integrand. So we can factor that 2 out if we like. We don't necessarily have to. It can combine with these constants similarly if we leave it in, but it might be nice to find the antiderivative of this function with the 2 factored out. Nonetheless, we're finding the antiderivative, or the integral of x cubed from 0 to 2. Well, what do we need? We need the antiderivative for x cubed. Well, what do I do to find that? I add 1 to the power of x here. So I'm going to have x to the 3 plus 1. And I divide by that new power. So here again, we'll see that the constants will just combine as we would expect. We might have written this as 2 over 3 plus 1 inside here. That's fine. This notation is a nice little handy piece of notation that gets introduced right away. And what this is telling us to do is, whatever this function is, this is capital F of x. We're going to do capital F of 2 minus capital F of 0. So it allows us to write this all in one line. So off to the side here, what this notation is really saying is capital F of 2 minus capital F at 0. This is capital F of x, this whole function here, with the 2 included. So that's that. Moving forward from there, we can actually do these evaluations, right? We know that this denominator is 4. 3 plus 1 is 4. We have x to the 4th here. 2 over 4 is 1/2 times x to the 4th. And I'll do 1/2 times 2 to the 4th minus 0 to the 4th. And I get this line in here. 2 to the 4th is 16 minus 0 is just 16 times 1/2 gives us 8. So that's our evaluation there. Now this, maybe I added more lines than students typically will use, or what I'll typically do for these problems. But this is a much less tedious way of calculating this area or this definite integral than using the limit of the sums. All right. So let's see what else we can do with it. Not only does it simplify our work with polynomials like x cubed or something times x cubed, but it'll also give us a pathway to integrate functions that aren't x cubed, x squared, or x to the first power, or a constant, which, in other words, don't have those nice number theory results of the sum of the first in integers or the first in integers squared and so on, because we won't know what to do for something like cosine or tangent. So let's see what we can do with this further. So the next problem asks us to find the area under the sine curve from 0 to b. That's interesting, where b is a number between 0 and pi. So we're gonna leave b as an arbitrary value, something that could just be decided so long as we select it within these parameters, so long as we select it between 0 and pi. That's some arbitrary constant there. And we're going to integrate from 0 to b the function sine of x, the area under the sine curve, or the area between the sine curve and the x-axis. It's another way to think about it, instead of just saying under. Now, in order to do this, well, I need to know the antiderivative of sine of x. Well, if we think about that, we'll remember that that's negative cosine of x. Remember, when writing down an antiderivative, you can probably check it quickly most of the time. So I write negative cosine of x down as my antiderivative, and I check, if I take its derivative, do I get sine x back? Well, the derivative of cosine x is negative sine x, so negative sine x is going to be positive sine x, so that works out. Now, my notation says to evaluate this from 0 to b. In other words, this is my f of b minus f of a expression from the notation before. If we think about the theorem as it was given on the previous page, it would look just like this. This is the antiderivative of b minus the antiderivative of a. In this case, a is 0. In this case, b is b. But those could be any numbers. So negative cosine of b minus negative cosine of 0 gives us negative cosine b plus 1. Cosine of 0 is 1, and minus negative is positive. Plus 1, or 1 minus cosine b is our answer here. This is interesting, just for a quick pause, because b, being any value we like, we now have sort of a function of b here that we can find the area between the sine curve and the x-axis for any b value between 0 and pi. So namely, we could use maybe pi over 4, or pi over 2, or even just 1 or 2 or 1.5, something like that. Right? And we could get area calculations for the area between this function, y equals sine x, and the x-axis for any b values between 0 and pi. That'll be relevant in the next section, thinking about this area function, or this integral as an area function. So let's move on to another sort of simple term or definition to dispatch before we really get into some more of the details of definite integrals. And that's the indefinite integral. So what we'll start to use, since we've already seen that a definite integral, which looks more or less like this, let's go back 2 pages and look at the beginning here. A definite integral, one with given endpoints a and b, is equal to the antiderivative of b minus the antiderivative of a, right? So taking the antiderivative f of x and evaluating it at b and a and finding that difference. So it more or less looks like the integral of a function is equal to its antiderivative to some degree here, right? The difference of its antiderivative. And that's really what an indefinite integral is telling us exactly. So the indefinite integral of a function, just because this is fairly handy notation to have around, is the antiderivative. So that's what this evaluation theorem sort of at heart is suggesting to us, that if we integrate a function and we don't have limits of integration, well, then that just becomes our antiderivative. So now we have a really nice notation for antiderivatives. So remember that we can check this by going the other direction. If I differentiate this function, I better get back the integrand, or the lowercase f of x, in that integral. So let's have a look at a couple of those. So evaluate the indefinite integral. This question is almost the exact same thing as saying, find the antiderivative of negative x plus 2x cubed. In fact, it is exactly the same. So when we evaluate an indefinite integral, we'll look for the most general antiderivative. So that means we'll add a plus c as usual when we did that in antiderivatives. So this indefinite integral is equal to, and I have the option here. I can do the antiderivative of this as one function. I can remember that I can split integrals over plus or minus signs. So I can split up sums in integrals, and I can factor out constants or negative signs in integrals. And that's exactly what I've done here. Again, I don't have to. I can find the antiderivative of this whole expression and go from there. That's fine. Or I can split it and work in these lines. So what I've done is I've split over the sum. So the integral of my sum is the sum of the integrals. And I factored out a negative from the negative x on this one. And I factored out a 2 from the 2x cubed. And now I can very easily apply a power rule to find the antiderivative of each of these terms. So I get 1/2 x squared for the first one with a negative sign out front. Then I get 2 times 1/4 x to the 4th. X cubed's antiderivative is x to the 4th over 4, or 1/4 x to the 4th. Now, maybe a little simplification here between 2 times 1/4, and that's just 1/2. And my overall antiderivative is negative 1/2 x squared plus 1/2 x to the 4th plus c. Now at this step, as soon as I've resolved all of my integrals, there are no more integral signs, I have a habit of writing a plus c. That's good. As long as it makes it into your final answer, then that's fine, right? All indefinite integrals should have a plus c because we want the most general antiderivative. Okay, let's look down towards the bottom here. Evaluate the indefinite integral. Okay, so this says Calc 2 off to the left. Let's ignore that for now, right? And actually, we'll ignore that in general. If you're interested in that, you might take a quick look and see how that works out. But we don't need it for this course. Let's just look at the function on the right, or how we might evaluate this function on the right. We're asked to find the indefinite integral of 1 over 1 plus x squared. All we have in Calculus 1 now is the ability to think back from a function, to say, okay, here's a function I'm given. Is it the derivative of a known function? And perhaps you go through the book, flip through all your old derivatives, and it looks maybe familiar. Maybe it's an inverse trig antiderivative, or it's the derivative of an inverse trig function. And you'd probably finally land on it and realize that, oh, y equals tangent inverse of x has derivative 1 over 1 plus x squared. So the antiderivative, or the indefinite integral of 1 over 1 plus x squared, is equal to tangent inverse of x. And then plus c to make that the most general antiderivative possible and have it be the indefinite integral. Remember, c is some arbitrary constant. If we take its derivative, it's going to be 0. So when we take this whole thing's derivative, we get exactly 1 over 1 plus x squared. Right, and this is just me checking using the techniques of this course that tangent inverse of x's derivative is in fact 1 over 1 plus x squared. That's not necessary to do. This method over here is just interesting to see how we might solve that in other ways in the future. If you're going on to Calc 2, maybe this is worth a quick moment to look at. If not, don't worry about it. There we have it. So antiderivatives and indefinite integrals are one and the same. And for now, all we can really do is just work backwards from what we know of derivatives. So to help us with that, you might want to have a table on hand that's similar to this one. This is also in the textbook, I believe, a similar table there as well as this. And this table is in my notes, of course, obviously here. These are properties. The sum property, where we can split up the integral over a sum. Here's the constant multiple property, where we can factor a constant out of the integral. Our most useful antiderivative or indefinite integral rule is this one. x to the n plus 1 over n plus 1, right, for the antiderivative of x to the n. And then so on down the line. E to the x's derivative is e to the x, so its antiderivative the other way is just e to the x still. Integrating 1 over x, right? This is the case where n is -1. So it takes care of that special case. We get natural log of x, because remember that natural log of x's derivative was 1 over x. And you can think through in reverse for all of these antiderivative expressions or indefinite integrals down the line and realize that, yes, over here I have a function on the right, on the left is that function's derivative. So if I ever meet a problem that says find the integral or the indefinite integral or the antiderivative of this function, then I just know that I need to try to find a function whose derivative is that function. So that's a pretty still primitive way of doing this, but it opens the door to a lot of different functions we can find the antiderivative of. Don't try to extend this too much beyond what we have on this table, right? These things are very delicate thanks to the chain rules and product rules that are in the backgrounds of all the derivatives we used to take. A lot of things that you think might carry over to indefinite integrals or definite integrals, like the chain rule or product rule, don't work in the way that you might think they do. So the inverse of those processes is somewhat difficult. Section 5.5 will do the inverse process for the chain rule. It's called the substitution rule. Calculus 2, you'll start by doing what's called integration by parts, which is the inverse of the product rule. So it's not an obvious thing to do to figure out how to take antiderivatives of functions for now. So don't try to apply anything more than what you know from these tables and these couple rules that we've got that we can use to manipulate the integrals of functions we might be trying to take. So this is a handy table to have around. Know that there are more functions that could make this, right? There are 4 more inverse trig functions. There are 4 more hyperbolic trig functions, so on down the line. But this is just a good starting point for a lot of these and maybe a handy thing to keep in mind. So, by the way, what happens to the constant of integration when we do a definite integral calculation, right? So back here, we found the antiderivative in this first example, yet we didn't write it down in its most general form, and we didn't take care to add an arbitrary constant of integration, right? Some constant that can be set to any value. Well, let me show you why that might be the case. In our specific example, we know that the antiderivative here was 1/2 x to the 4th once we integrate or find the antiderivative of 2x cubed. So let me write this as an indefinite integral and we'll think it through. The indefinite integral is really nothing more than the antiderivative, if we remember. And we've already seen in this example here that you can calculate this to be 1/2 x to the 4th. And I'll put plus c. So that plus c, again, it's any real number, right? We can arbitrarily decide it to be some number along the real number line, and it's always going to work as an antiderivative or as the indefinite integral of 2x cubed. Now, let's do the definite integral based on the indefinite integral. So the indefinite integral is a step in the definite integrals calculation. You find the antiderivative. So if I wanted to evaluate from 0 to 2, 2x cubed dx, just like I've done before, well, I know it's going to be f of 2 minus f of 0, capital F being the antiderivative of this function, or in other words, the indefinite integral. That's one way to say it. So now if I use this as my function for capital F of x, let's see what happens. I'll have my first evaluation will be in brackets. It'll be 1/2 times 2 to the 4th plus c. So that's my first one in brackets. And then minus 1/2 times 0 to the 4th plus c. And what have I got here? This is f of 2, capital F of 2, with its arbitrary constant of integration. Capital F of 0 with its arbitrary constant of integration. I wrote down my most general antiderivative. When I distribute this minus sign, let's see what I have now. I have 1/2 times 2 to the 4th I'll write that as 16 then, plus c, minus 1/2 times 0 is just 0, and then minus c. What happens to my c values? They add to 0, and they disappear from the expression. I have 1/2 times 16 is 8, plus 0, minus 0, whatever, right? It's all just zeros from there. So I have an 8, and I get the same exact value that I got first time around. So that's why in a definite integral, we don't have to worry about writing down our most general antiderivative. It just doesn't matter, right? So there we have it. And that will happen. We could have done this in the most general case up here, written all of this out, and we'd see that the f of b plus a c minus, in parentheses, f of a plus a c. The c's would add to 0 once again, and we would just have f of b minus f of a in general, and that will always be the case. So that's a nice thing about definite integrals, is you don't have to worry about constants of integration. Okay, so moving on from our table here and getting into some indefinite integrals that we can evaluate. These things pop out somewhat quickly once you get the hang of it. So this first one, the integral of 8x cubed minus cosecant squared x dx, right? Again, think of the differential here as letting us know what variable we're integrating with respect to. That's for later calculus courses. That's more or less what this will do for us. For now, we think of it as the rectangle widths, right? These are infinitesimally small rectangle widths. Really, it's just a necessary part of the integral notation, and we'll just leave it at that for now. We're always going to have a dx there. When we have this situation, we find the antiderivative, and we're able to move on, and that's all we need to know about it. So the antiderivative of 8x cubed, we can do these in two different parts, right? 8x cubed, well, we add 1 to the power 3 here, we get 4. We're going to divide this by 4, so we're going to have 8 over 4 x to the 4th. That's 2x to the 4th. I didn't write all the steps out because we can start to do these this quickly. Now, for negative cosecant squared x, this one might be harder to recall. But if I go back to the previous page and scan through here, this one happens to be on the table. Right? This actually, we have all 6 trigonometric functions with their derivatives written underneath an integral. So we can go backwards for any one of these functions, right? So if this one shows up, right, our antiderivative here, well, then we know what to do with it. Now we have the antiderivative or the indefinite integral of negative cosecant squared x. So all I have to do is maybe change this formula by multiplying a negative on both sides, and that'll leave us with a positive cotangent x. We don't have to change the constant sign because it's just an arbitrary constant, right? If it was plus c, then maybe we'd call it plus c sub 0. It's any real number, positive or negative. It doesn't matter if we if it's minus c or plus c or whatever. So we'll always just write it as plus c. And that's what we end up with here, right? The antiderivative of negative cosecant squared x is positive cotangent x. We write a plus c when we're all done with it, and that's all we need to worry about. Okay, the next one, the antiderivative of 1 over square root 1 minus x squared. That looks suspiciously like an inverse trigonometric function's derivative. And then plus 1 over x, that looks suspiciously, well, that's natural log of x's derivative. So that comes out exactly as we see it. This one integrates to sine inverse x. This one integrates to natural log x. All of our integral signs are gone by now, so we just add plus c. Okay, again, we can do this as integral and integral for each of these functions here, splitting them up, or you can just do it along the line. It means the same thing to just write them down as a sequence plus each other, and you'll have the same results. And if we look on the previous page, of course, here's the first one connected to it. Of course, remembering these is going to be necessary. But remember that to recall these is not much work because we already know them in the other direction. So there we have it. The last one here is e to the negative e to the x plus 4x dx. So negative e to the x, well, I can ignore the minus sign and just hold it out front. The antiderivative or the indefinite integral of e to the x is e to the x. And then with the minus sign, it's just negative e to the x here. The indefinite integral of 4 to the x dx, that one might be good for the table, right? I'll go back and check just to, because this one can be a little confusing. I have a to the x, in this case I have 4 to the x, right? Is equal to, its indefinite integral is a to the x over natural log a. This one might be the only one that's a bit of a surprise, to some degree, only because this constant looks a little different. Just remember that the derivative of a to the x is equal to a to the x times the natural log of a. Okay, and if that was the situation, if we want to go backwards, then, well, who's who here? This is the antiderivative. So if I write this down like this, d dx of a to the x over the natural log of a, this looks like I'm just checking this to make sure its derivative is that, and that's exactly what I'm doing. What I get is a to the x natural log a, because that's its derivative, divided by the natural log of a. These cancel, and I just get a to the x. So that's why this works out the way it does. The antiderivative of the exponential function a to the x is a to the x over natural log of a for that reason. In other words, for any one of these, to check why these are the antiderivatives, all you have to do is take the derivative of the function on the right, and you'll see that you get the function on the left, provided you do it correctly. So there we have it. A is 4 in this case, and we just apply the rule as is. Once all the integral signs are gone and we found all of our indefinite integrals or antiderivatives, we have a plus c. So moving forward, let's think about what the definite integral is in terms of possibly applied problems. So in a lot of cases, the derivative of a function can really be thought of the rate of change of some situation. The rate of change, maybe the change of position versus time, that would be a velocity function, right? Or population versus time, things like that. If we take the integral of a rate of change, what we get, and this the definite integral from a to b, what we get is the net change, or the net displacement if this is a velocity function. Okay, so let's see what this looks like in practice. This is the same formula, right? Only now we're saying f prime of x in here. And this is all the more compelling to us that the integral is the opposite of the derivative. Look, I'm integrating this function f prime, and what I get out is the function f. So the integral, in some sense, undoes the derivative to give me the function that's in there. So we'll see more on that in the next section. Okay, the equation below gives the velocity of a particle at time t. So v of t is equal to 3t minus 5. It's our velocity equation. The thing to remember about velocity, v of t, is it's equal to our position function, s prime of t. So the derivative of our position function, s prime of t. And t ranges from 0 to 3. And part A asks us to determine the displacement of the particle, not the article, the particle during the time interval. So in other words, we know it moves at this speed, and we're going to observe it from time t equals 0 to time t equals 3. What is the net displacement, or what is the position of this thing over that time? So the displacement meaning the net change in position, or the net position of it. So if it moves to the right 2 units and then back 2 units, its displacement is 0 in the end, right? It's back where it started. So that's, just recall what displacement is. It's the total movement of the particle, or whatever it is we might be observing, from one time to the next. It's just the end result of where the thing has moved to. Now, so our displacement is our net change, as I just described them. So what we do is we'll take the antiderivative, or the definite integral, from 0 to 3 of our velocity function, that will give us a position function that we evaluate at 3 minus its evaluation at 0. In other words, we just apply this rule to it. So 3t minus 5 has antiderivative 3/2 t squared minus 5t. We're going to evaluate from 0 to 3. So that'll be this function of 3 with t equals 3 minus this function with t equals 0. And that's happening right here. That's this function with t equals 3. And here's that function with t equals 0. And we take the difference, f of b minus f of a. F of the top of the right endpoint minus f of the left endpoint. This one's just 0. And when we simplify these numbers, we get negative 3/2. So what this thing tells us is that the particle has changed. Its net change in position is that it is negative 3/2 units from where it started. So if this was left or right, and to the left is negative, then it has moved in time t equals 0 to time t equals 3. From where it started at time 0, it is now negative 3/2 units to the left at time t equals 3. It might have moved through a lot of other terrain in between there, but by the time we look at it again at time t equals 3, it is now negative 3/2 units away from where it started, or 3/2 units to the left of where it started. Right, now, part B says determine the distance traveled by the particle during the time interval. Now you might say, well, that's just the same, right? Its distance will be its displacement. But remember, like I said, it might have chosen a very roundabout, erratic path to move negative 3/2 units, or in other words, 3/2 units to the left. It might have started by going to the right some ways, and then back to the left some ways, and then back to the right a little bit to have a net displacement of negative 3/2. So we don't really know that until we look closer at this problem. So the way to think about this is we need to see where we really want to calculate the absolute value of the integral of this function, we want to calculate the integral of the absolute value of the function. Distance has no direction, so it doesn't care if we move positively or negatively. Displacement does, same with velocity. So what we need to do is integrate. This could be thought of as the speed of the function. And what we're really thinking about is this. Say we're in a car, right? We're going to move forward. We're going to move backwards. The odometer is going to register distance no matter what, if we move forward or backwards. So we'll get the total distance that we moved in this car by integrating from 0 to 3 and making our integral positive. Okay? Because what happened up here potentially is this function might have been negative for parts of the interval from 0 to 3, and it might have been positive for other parts. And overall, and all of that added together, remember we'll get negative area and positive area. When it all added together, we came out to a negative 3/2. So let's get rid of all those negative possibilities by taking the absolute value. Now this makes it look a little simpler than it actually is. When I integrate from 0 to 3, the absolute value of a function, I actually need to split this interval up in a way where I take care of or evaluate or explicitly handle the absolute value. So what I need to check is, where is this function negative and where is it positive? So in order to do that, I'm going to say, well, when is it 0? Because if I find where it's 0, I'll check to see where it's negative and where it's positive on either side of that 0. So to find when the function's 0, I set it equal to 0, and I solve for t. This is easy. I get 5/3. There's only one place where this function is equal to 0. So there's only going to be one place where it's negative and one place where it's positive, if it's either of those, right? So it could be positive in both places. This is a line, so of course it'll be some negative, some positive on this interval, it looks. So how do I know where it's negative or where it's positive? Well, those are going to be test values, right? So maybe an easy test value is 1 to the left of 5/3 and 1 to the right of 5/3. So I don't know, 0 is to the left of 5/3 on the number line. And it's just an easy number to plug in. So 3 times 0 minus 5 is 0 minus 5. that's negative. So from 0 to 5/3, my function's actually negative. The output of 3t minus 5 is negative. In order to make that output positive, as the absolute value would have it, I need to multiply all of those negative numbers that come out of this by a minus sign. And that's exactly what I've done right here. Now I've also factored that minus sign out of the integral already, but nonetheless, it's the result of knowing that this function is negative from 0 to 5/3. So I need to put a minus sign times all these numbers to make it positive. Now from 5/3 to 3, you probably suspect correctly that we're positive along this. So I try t equals 3 here for this function. And 3 times 3 is 9. 9 minus 5 is 4. It's positive on this side. I don't need to do anything here other than just write my function down as is, right? If the numbers that are coming out of this function are positive, then the absolute value bars do nothing. They just let the values come out as they are because they're positive. So now that's the interval from 5/3 to 3. And if I look at this, I remember my properties of integrals. This integral plus this integral is the integral from 0 to 3, because the upper endpoint of this one matches the lower endpoint, and they sort of glue together or paste together to make up the entire interval cleanly. So there we have it. We've handled the absolute value that's in here by splitting up the interval and writing our positive portions of the function down as is, no changes, because that's how absolute value is going to handle it, and taking our negative portions of the function, putting a minus sign in front so that the overall result will be positive. Now, how does this come out? Looks like we've got more work on a subsequent page. We're going to integrate each of these functions as we have them here. Here's just another copy of it. And we start to work, right? We need to find the antiderivative of 3t minus 5. Well, that's going to be 3t squared over 2, or 3/2 t squared, minus 5t. Minus 5t. And there's not a lot of extra work. There's a lot of extra writing for this, because this one's antiderivative, same function, is just the same antiderivative. The only difference is there's a plus sign here, and there was a minus sign in front of this one. And we have to keep these separate because, well, this one's negative, whereas the other one's not. We have to do these endpoint evaluations and these endpoint evaluations on their own, again, because this function's positive and this one's negative. So we continue along. Here's my evaluation of the endpoints in the next line. Here's the minus sign in front of that term. This is this function of 5/3 right here, minus this function of 0, which is right here. Plug in 0 to this, you'll see you just get 0. And that is, in this first bracket, the integration or the evaluation here for this term. The other thing that we're adding to this is the evaluation of this function for these limits of integration. Again, it's not hard work, it's just extra stuff to do. So this function evaluated at 3 is here, minus that function evaluated at 5/3, which is here. And this now is just a bunch of simplifying arithmetic, right? And when we get down through all of these steps below, you might pause here and make sure that you can work this out to get the same value. We'll find that we get 41/6 is our distance traveled. And I just renamed what it was to remind us what it was. Remember that our displacement was -3/2. Our distance is a different value. And that's because, again, we don't take into account direction when we talk about distance. We're just talking about the total distance that the thing has traveled versus its net displacement, which is where it ends up after it's done traveling. So if you were to travel from your hometown 300 miles away and then return, your displacement is 0 from the beginning to the end of that trip, because where you ultimately ended up is the same place you started. Your distance is 600 miles. You went 300 miles out, and then you went 300 miles back to get home, and you traveled a total of 600 miles, even though your net displacement is 0. So those are the two differences between distance and displacement. And of course, that's why those two numbers are different. So there it is. That's our one of our most basic integral as a rate of change, or integral of a rate of change, yielding the net change examples. The book has a few with population and power calculations and things like that. And speaking of that power calculation, I do one that's fairly similar here. So these are endpoint approximations, and it's just another way of interpreting what an integral actually is. So we go back to this approximation situation, and we're given a table of power consumption, right? This is just we're going to show, I think at least there are at least several different uses or examples of this in the textbook, and in examples in any live meetings throughout this course, or any Calc 1 course, but this is yet another nice one. So we have a table of power consumption for a city in one 24-hour period, and we're asked to estimate the total energy used on that day in that 24-hour period then. So we have the time in hours, T here as 0, then 4, then 8. Looks like we have 4-hour intervals at which we've observed the power output of our power grid or power plant, you might think of. And then we have the actual power output at those moments. So the amount of power that's being output are these units here, or these values here, in units of megawatts. So power, if you recall from physics, is energy divided by time. It's the rate at which energy is delivered. And if you think about what power actually is, that should make sense. When you get a power bill, you're actually getting an energy bill, because what you've done is if you've used some amount of kilowatt hours, or divided by or per some number of hours, and kilowatt hours divided by hours is kilowatts, and kilowatts is a measurement of power, right? Or so, yes, power, kilowatt. So I jumped the gun on that one. Power is energy divided by time. That's right. It's the amount of energy you use per time, right? So if you need a lot of energy in a quick amount of time, a short period of time, then you need a large amount of power to do that. Think about a car starting from 0 in its acceleration, how much power it needs to start moving that large mass. Now, solving for this equation, or solving for energy in this equation, we get the equivalent equation: power times time equals energy. I've just multiplied both sides of the equation by time. Now, this is what I was trying to say before. Power is measured in kilowatts, right? So, or watts, or, watts, I guess, would be the basic unit of measure. But since we know kilowatts from our power bills, then kilowatt hours is kilowatts times hours, or power times time. So a kilowatt hour is actually a unit of energy. Typically in physics, energy is measured in joules, but it's reasonable enough to say kilowatt hour, because a kilowatt hour means the kilowatt times an hour, and that's power times time. That's where that unit of measure comes from. Okay, all right, that's a bit of a divergence, but let's get back to the task at hand. We want to estimate the total energy used on that day. Notice we don't have a perfect function, P of t, P as, or P prime as a function of t, or the power as a function of t, and then an integral that we could do on that function P. So what we'll do is just endpoint approximation based on the table values. So we'll use left endpoint approximation, and we'll note that delta t, our time steps, are in units of 4. So set that up, and our energy use will be approximately the sum of the delta t's times the power output at each of those endpoints. We're going to use left endpoint approximation, so we'll take as our 0 to 4 interval the value 440, right? We'll take as our 4 to 8 interval energy or power usage as 400. 8 to 12 is 420. 12 to 16 is 620. And when we get to the very end, we just note that 20 to 24, we use the left endpoint's value of 680. If we did right endpoint evaluation, all of that would be different. We would go 0 to 4, we would skip that left endpoint, and we'd use our right endpoint. And we'd do that all the way to the end using 500 in that case for the right endpoint approximation. Those approximations will be different from each other, but nonetheless, we could use them both as two different approximations. So here we are, 4 times 440 plus 4 times 400 plus 4 times 420. I'm just multiplying 4 times each of these numbers and stopping at 680 because that's my last left endpoint. So get rid of all these highlights and we'll see what comes out of that. Well, all of these added up, each times 4, I've just factored the 4 out of there since all my delta t's are the same size. I've written this down in a more simple way. The sum of those numbers is this times 4. And whatever this comes out to, it looks like I did this by hand for some interesting reason. And nonetheless, I get 13,440 megawatt hours. Remember, these units were in megawatts. This is times 4 hours. So megawatts times hours is megawatt hours. And that's our sort of known power calculation. Kilowatt hours, megawatt hours, watt hours. That's how we measure electrical energy or electrical power. Sorry, electrical energy typically. So again, by the way, if we had a function of P of t, which was the power usage at any given time t, and we did the integral of P of t with respect to t, or dt here, and we went from time 0 to time t equals 24, then what we would get out of this is the total energy that's used. Or the net energy that's used, but the power grid really is nothing but positive values here, so we're going to get the total energy, right? Unless people on the grid with solar panels might be able to feed energy back towards the grid or power plant in some sense, but that's a bit of a distracted thought. Okay, so last question here is just that point of caution that I talked about at the very beginning of the notes, and that's this. We have an integral 1 over x squared with respect to x, or dx, and it's a definite integral from -1 to 3. Now, if I'm not careful about this, and you can see in the graph off to the left that really I should be careful about it. If I'm not careful, look what kind of trouble I can get into. -1 to 3, x to the -2 is 1 over x squared. So I find x to the -2's antiderivative. I add 1 to -2 and divide by that result. I get x to the -1 divided by that -1. So I get a pretty good looking antiderivative. I'm pretty happy with that. I continue working on this. I'm going to evaluate from -1 to 3. So I'm going to do this function of 3 minus this function of -1. And that's going to be negative, right? So that's going to be -1/3. So -1/3 minus -1 over -1. So here's that portion, minus -1 over -1. It's a lot of things going on there. This minus sign right here, by the way, is from the f of b minus f of a definition here. So that's why that one's there. This minus sign is from this portion. And the fact that this is a -1 comes from that. So to help with those details, since that's a little confusing looking. 3 minus signs make that negative. This is negative. And I continue to work in a way that is, well, going to be a little deceiving possibly, right? Really, however you want to finish this up, we get to -4/3. I think we could see that right here once we resolve that. -4/3 is what I think might be my answer to this integral. So our signed area, remember area that can be positive or negative, which would be for any definite integral now, happens to be -4/3. But I made one critical mistake here. Go back and look. 1 over x squared, sure, it's continuous on all of its domain because it's a rational function. However, part of its domain, well, the number that's not in its domain is 0. 1 over x squared is undefined when x equals 0. However, this interval includes 0. So this function is not continuous at 0. It's not continuous on this interval. My evaluation theorem to get this number is not appropriate. I've used it, I've gotten a number, and I feel good about it. However, I've made a huge mistake. It was never applicable in the first place because this function is not continuous on this interval. Remember what 1 over x squared looks like as a function. It's got a vertical asymptote at x equals 0. And if we integrated here from -1 up to 3, and we could have, we don't really know what goes on here. There could be an infinite amount of area in there. There might actually be a finite amount of area, and this might, for other reasons, come out to some value that is actually correct. But moreover, something looks all the more suspicious about this. We got an answer of -4/3. And what do we know about 1 over x squared? It's always positive. How did we get negative signed area for a function that's always positive? So that should be the other clue that this is completely wrong. This did not work out the way that we expected it to. And this rule is not appropriate to use on this function because of that vertical asymptote. Now, Calc 2 will allow us to build, will give us some tools to help us determine whether or not the area that's pressed up against this vertical asymptote is actually infinite or finite, so that whether or not the integral converges or diverges. But for us, we just have to say, well, this thing is undefined, the function is not continuous here, so I can't use this evaluation theorem. Because remember, that was one of our main conditions, was that the function in here is actually continuous on this interval. If we have a vertical asymptote on that interval, we're certainly not continuous. So there it is. That's section 5.3, definite integrals, a little bit of indefinite integrals, and then an interpretation of definite integrals as net displacement or net change.